When we have to move on with our discussions or our journey of learning about electronics communication laboratory. This is Olenjolain. I thank God by His own grace. I'm a local and national teacher who is actually trying to transform the mind of students in our beautiful country, Tanzania, and also even outside of the boundaries of our country. I would like to take this opportunity to welcome some physical, electronics, and telecommunication engineering students who have joined to us into this interesting moment. And we are here in order to help you, and we are here to teach you what we know. So I would like to tell you that this is a serious program. You have to be connected, you have to listen, you have to pronounce some terminology that we are going to discuss. You should be active, simply that's what we call it, because an engineer is always serious and real committed in order to maintain safety for anything. So these are the intermediates. It's a fundamental skills that I'm going to teach you, but also it's intermediate. And this module, in some parts, it actually has has the same contents as the contents that covered in fundamental digital electronics. So you should not be confused with that if maybe we are learning the same contents that maybe I've covered it previously. So for me, I thank God I'm ready in order to teach you. How about you? How about you, students? You are ready. How are you, students? How are you? Are you happy to learn Bachelor in Electronics and Telecommunication Engineering? Are you happy? Yes. Okay, for me, I'm happy to teach you. So today we are going to start a new topic. The module is called Electronics Communication Laboratory. In this module, we have to cover theory, simulation, and the hardware implementation or practical. This is chapter 5. Students, read it. Read chapter 5. What the chapter? What the chapter name? Measurement of 40 digital signals in digital electronics communication circuits. But even if you omit the word communication, it's fine. Okay, because communication, digital communication, it's just one of the applications of the digital electronics. So let us do the quick review of what we have discussed. Quick review of what we've discussed in workshop 4. So in workshop 4, what we have taught you actually, we have taught you we have taught you about analysis of 40 of pull down resistor network. Pull down resistor network. And this network is very interesting because it consists just of the DC power supply. It consists of a push button, but the push buttons may be replaced with any digital sensor or some other sources of the digital signal. And also it consists of a class resistor. This resistor is called the pull down resistor. It's a normal resistor, but when we use it in that aspect, it will be pulling down the voltage or the power or the DC power. Then the next one, or the next concept that we've discussed after we have done analysis. Actually, we found 4 theoretical values. We've been finding the voltage across resistor when the push button is not pressed. And also we deduced or we calculated how we find the voltage across the push button when the push button is not pressed. Again, we discussed that how we can compute voltage across resistor when the push button is pressed. And also discuss how you can compute voltage across push button when the push button is pressed. Are we together? Again, after discussing about that, we opened the block of sum. And then we said we may have different digital electronic circuits that actually will be connected to the output of the exclusive OR, and it will be actual it means it will be performing logical operation with the sum of the 2 binary inputs which have been summed by, or which have been added together by the exclusive OR gate. Hey! In quick review. So we say that to simplify, for this case, we are going to have some indicator. And then we say that in this indicator that will be indicating the sum, we say we are going to use just the LED. And then we open the block that written Scotty carry. Once you open this block, we say also we are going to present this carry indicator. Then after that, we have opened all the 5 blocks. Okay? No. There's another block that we opened, but we did not have a discussion about it. And this is about DC power supply unit. It's not DC to AC or AC to DC linear power supply. This is DC power supply unit. We just see due to the schematic, we did not discuss. But hopefully maybe today we may discuss it if we have time. Also, we discussed about it. After that, we drew the overall schematic circuit logical circuit diagram of what? Of the half adder. And this one we drew as how we used to draw on paper and also on simulation. We did not touch some other important information because we didn't cover this topic. And then finally, we drew the overall schematic logical circuit diagram of half adder, but in hardware implementation. And hopefully, I believe that all the students, or a large number of students, have enjoyed it because they have never thought about that. They are expert on drawing the schematic circuit diagram on paper and also on simulation. Boniface? So today we are going to discuss about measurements of the digital signal in digital electronics communication circuit. So let us continue. So in case you missed the workshop number 4, workshop number 3, excuse me, you can access in our official YouTube channel that called online, Bachelor Polytechnics of Tanzania. However, that shortly we are going to change the name of that online school. So today we are going to discuss about the measurements of digital signals, and these digital signals in digital electronics communication circuit. So first of all, we say that, let us start with this sentence. So the digital signal is always DC in nature. The digital signal, first of all, is always DC in its nature. So you say that all the measuring instruments of all the measuring instruments used in digital electronics must be DC. Case that its utility must be DC. Case that it uses power or. So these are the key points that you have. So he said that in digital, so he said that maybe classes of measuring instruments, used in digital electronics. So in digital electronics, there are two main classes of the measuring instruments. And these, we name them namely as, the first one, we have basic digital measuring instruments. And the second one also have advanced digital measuring instruments. Class A, basic digital measuring instrument. Again, say loudly, basic digital measuring instrument. Say loudly. Samuel, Ringo, say yourself. You are not in the class. Pardon? Say basic digital measuring instruments. Say basic digital measuring instruments. So when you talk about digital, stop writing. This word digital representing the nature of the signal that will be measured by those instruments. However, that also these measuring instruments are digital. They are not analog. Are we together? So this word of digital, mainly it's real insisting about the nature of the signal. And this word called the it means that the instrument itself will be digital, and also once the instrument will be digital, also the signal measured will be digital also. But for that case, it's actually representing the nature of the signal measured by this measuring instrument. The second one is called the advanced digital measuring instrument. Say advanced digital measuring instrument. Robert, say yourself. Eh? Class, say again, advanced digital measuring instruments. So let us start with the first type or the first class, basic digital measuring instrument. Digital measuring instruments. So the basic digital measuring instruments is a set of measuring instruments that are used to measure basic electric parameters such as basic to measure and display display the basic electric parameters. Basic electric parameters. And this display the waveform, sorry, to display the waveforms of basic electric parameters such as current, voltage, and the power. The following are some examples of basic digital measuring instruments. So we have voltmeter, simply say that DC voltmeter. Say DC voltmeter. Class A DC voltmeter. And also we have DC ammeter. And the third one we have digital oscilloscope. Digital oscilloscope. So you say that, let us discuss one after the other one. So DC voltmeter, say DC voltmeter. So the DC voltmeter is used to measure the potential difference between the 2 points. So the DC voltmeter is used to measure the potential difference between the 2 points of the testing point along the digital circuit. So simply say that in digital electronics, we are using only 2 types of DC voltmeter. And these types, the first one is called the DC voltmeter which is actually measure voltage in terms of volt. The second one that we are using is DC millivoltmeter, which will be measuring the voltage in terms of millivolt. Then now, let us have discussion on DC ammeter. Say DC ammeter. Say DC ammeter. Again, say DC ammeter. The DC ammeter is used to measure the amount of DC current that flows through, or used to measure the amounts of DC current flowing in a digital electronics circuit. So simply this one will be measuring amounts of direct current that flowing in a digital electronic circuit. But also remember that we always connect the C ammeter at a testing point along the circuit, because a digital electronic circuit will have different testing points which have meaning. So it means that in case of ammeter, before you use a DC ammeter to measure the current flow in a digital circuit, you have first of all to choose the testing point. And I think that this is just to remind you, however, that I know you know it, but it's better to remind you because possibly you have forgotten. We say, so both DC voltmeter, and the DC millivoltmeter are connected across the 2 points. Simply say that this is connected in parallel. We taught you this concept in the second topic of physics from 2, which is called the current electricity. We introduced you, but possibly you have forgotten it. Where are you going? Call some other students who are late like you. When you reach 5, you'll get in. So check who is not in and then call him. So he said that both the DC voltmeter and the DC millivoltmeter are connected, across. Say both the DC voltmeter and DC millivoltmeter. Say it. Stop writing, because others are writing. Say both DC voltmeter and DC millivoltmeter are connected across the 2 points. The 2 points of what? Of the particular testing point. Remember that this is another question that I have to give you. Alawi. We used it to get in. We used it to use, or we used it the voltmeter to measure voltage across a resistor. This, stop writing. In O level and A level, we taught you in most cases that how we can use a voltmeter to measure voltage across, or the potential difference between point A and point B. And in between of these 2 points, there is a component which is called maybe resistor or capacitor or inductor or a diode. That's what we have taught you. So remember that in case of this of electronics, sometimes the DC voltmeter is not used to measure voltage across the electronics component, but it is used to measure voltage at a particular point. So for instance, this one. And for this case, these 1 points will be connected to the positive terminal of the voltmeter, and the negative terminal will be connected to the ground. So do you see that these are the 2 different configurations? Are we together? Are we together? Are we together? So it's better to understand what you want to measure. The issue is not the testing point, because this is, we used to call that, maybe this is testing point T, let's say Q. So testing point Q, it's actual point A and point B. Together we call them one testing point. Are we together? For this case, this one we can call T testing point P. So it means testing point P, within it, it has 2 points. P, or it means that the one terminal of resistor and the ground. Are we together? Class, are we together? It's not clear.
Not clear.
Not clear. Thank you. Listen. For instance, let me remind you something we taught you in analog electronic circuit. Precious? In analog electronic circuit, you say that in order to bias a transistor, we need to have a base resistor. So the one who said not clear loudly, Bundala, now he's talking. He's not listening. So this is NPN bipolar junction transistor. And this one we call T base what? A base resistor. And then for that case, so for that configuration, you say that the emitter terminal might be connected to the ground, so might be connected to the emitter resistor. If you do remember that, at this point we had two testing points. The first one, we named it a particular letter. Let's say A. So this A, it's a testing point where we measure base voltage, VB. And VB should be measured across this resistor. Are you together? Are you together? But also, we say that, okay, fine. This is what VB. And then we say that, suppose we had the connections that this connects towards the ground. Then we say that within this testing point, we can use a voltmeter to measure VBE, voltage across base emitter. But this one will be between the base of the transistor and the emitter of the transistor. But for this case, the emitter is connected towards what? Towards the ground. So you can see that these are the two DC voltmeters, but this is connected across the component. Even this one is connected across the components, this transistor component, but one of the terms of the components is connected to the ground. So what I was telling you, sometimes depends on the circuit. You might need to know the voltage drops at this point, so you need to have a voltmeter. So the positive terminal is connected here, and the negative terminal is connected to the ground. That's what I was teaching. Shane, come please with your stuff. Hurry up. Now, is it clear? Is it clear? Is it clear? So you should not claim that maybe a voltmeter should be connected across the component. No. And also don't expect that the DC voltmeter will actually perform the measurements if just you just see connecting one terminal. No, it won't. Okay, the DC ammeter is used to measure the amounts of DC current that flowing in a digital electronic circuit. Are we together? Eh? Eh? Okay. And then we say that, remember that the DC ammeter or the DC ammeters or ammeter, one or more than one, must be connected in series. With what must be connected in series. It means along the digital electronics circuit. So this one should be connected in series. So the following are the DC ammeters that are used to measure the digital signal along the digital electronics circuit. So the first one, we may have DC ammeter. Class, say DC ammeter. Say DC ammeter. The second one, we may have DC milliammeter. Say DC milliammeter. The third one is called the DC microammeter. Then the third basic measuring instrument is called the digital oscilloscope. Or simply called the oscilloscope. Say digital oscilloscope. What the primary function of digital oscilloscope? Dixon? Macha? What the primary function for digital oscilloscope? Can you speak loudly? I don't hear you at all. Glory, can you amplify what he has been saying? Huh? Can you speak loudly? According to Dixon Marchand. The digital oscilloscope is used to do it. Glory, tell us again. I didn't hear. Let me just come closer. Oh, Dennis, can you amplify the signal? What did Dixon say? So Dixon Watcher, send the input to the control unit. Glory, what did he say? The digital oscilloscope is used to? That is Engineer Dixon Macha. So the digital oscilloscope is used to display and measure the magnitude of the digital used to display, sorry, that sentence is not complete. The digital oscilloscope is used to display the waveforms and measure the magnitude of the digital signal processed in digital electronics circuit. So the primary functions of digital oscilloscope are to display the waveform of the digital signal and also to measure to measure the magnitude of the digital signal processed in digital electronic circuit. Are we together? Are you together? Eh? Okay, so this is the simple work. So mention other three basic digital measuring instruments. And you have to explain what do they do in digital circuits. Advanced digital measuring instruments. So with this one, we say that these are advanced digital measuring instrument. That are used to measure different electric parameters. Different electric parameters that are used to measure different electric parameters. Different electric parameters processed in digital electronics circuits. Dominic, leave that place, go back to your place. So the following are few examples. The following are few examples of the advanced digital electronics. The following are few examples of the advanced digital measuring instruments. The first one, we call it SPI debugger. Class A SPI debugger. Say SPI debugger. SPI, this is very important. Stop writing. SPI is a very important phenomena in telecommunication, especially with microcontroller, with Node MCU, with microprocessor. Why? Because SPI, this is one of the communication protocol that's used in embedded electronics. And it's an abbreviation of serial peripheral interface. Say serial peripheral interface. Later on, when we'll be learning about counters, we have 4 types of counters. The first types of counter, we call it serial in, serial out. So CISO. Then you have serial in, parallel out. Then you have parallel in, serial out. And also you have parallel in, parallel out. These are the 4 types of 40 of counters. So in case of serial in or serial in, serial out, or serial in, it means that if I have 3 bits, and then these are the channels or these are the paths. If the serial peripheral will be used, so the 0 bits will be allowed to flow from one point to another point, and then followed by by 1. But if it is parallel, then 0 bits, for instance, will be passing through this path, and the 1 bit will be passing through this path. Are we together? So when you call it a serial peripheral interface, this is the type of telecommunication, electronic communication interface whereby the bits will be traveling or will be moved or will be traveling from one point to another point as a series, as a sequence of bits. Are we together? Are we together? Are we together? So you have serial peripheral debugger. Say serial peripheral debugger. Say serial peripheral debugger. And then the next one is called the logic key analyzer. Say logic key analyzer. Say logic key analyzer. Say logic key analyzer. Then the third is called the visual terminal. Say visual terminal. Say visual terminal. The next one is called the spectrum analyzer. Say spectrum analyzer. Say spectrum analyzer. Then the next one, we call it the pattern generator. Say pattern generator. Pattern generator. Then the next one is called the, this is pattern generator. The next one is called the counter timer. Say counter timer. Say counter timer. But because this module of electronics communication laboratory, it's a fundamental module, we are going just to discuss about how we can use the 3 basic measuring instruments that I have taught you to do the measurements at different testing points. We are not going to discuss about advanced digital electronics instrument, but I've mentioned or I've introduced you the concept in order to be familiar that there is something else that you can make a follow-up. Are we together? Are we together? So now let us keep on focus about measurement. Measurement of so measurement of 40, measurement of digital signal or digital signal, different digital signal. Different digital signal. So measurement of different digital signal with so measurement of different digital signal in half order. So in previous workshop, which was workshop 3, we drew the overall schematic circuit diagrams of half adder as well as when we draw it on piece of paper or on simulation software. So right now we have to redraw it again, but we have to choose testing points in order to connect it the DC measuring instruments. So let us start. This is the ground terminal. And then we start from the DC power supply unit. Class A DC power supply unit. So this is the first testing point. Why should it be the testing point, the first testing point? Because theoretically, it has been written that the battery that you are going to use, it provides 9 volts. But you have to measure because sometimes it's not 9 volts. But the manufacturer wrote that this battery will provide 9 volts. But maybe somebody has used it, so there is a actual deductions or decrease of 40 potential drop or potential energy stored by that battery. Are we together? So maybe in your calculation you may say that I'm using 9 volts, while practically you're using 7 volts or 60 volts. Or maybe you can find your system is not on. But you don't know, you will be trying different ways to check the problem. So maybe the problem is just the battery. Because if the battery is not working, the entire system will not work. Are we together? Class, are we together? Yes. So this is our first testing point. So where we are very interested, and this the parameter we can measure. We can measure just the supply voltage or voltage across, or this we call it potential, or we call it electromotive force. Say electromotive force. When a battery is not used, when you measure the potential difference between the terminals, that we don't call it potential difference, we don't call it voltage, we call it electromotive force. We call it voltage or potential difference when there is a driving of current. Are we together? So we covered that in physics form 3 about electromotive force and potential difference. So this is our first testing point called the A. Okay? Okay? And this testing point is about this point and this point. So together we call them one testing point. Stop drawing, please. I gave you time to draw and you know what you've drawn. Then the next step after having the DC battery, the DC battery, then next step we need to regulate this 9 volt or 7 volt or 8 volt into what? 5 volt. So for this case, because this one we draw just on paper or whatever, in Proteus, the voltage regulator is not written as LOM 7805. It's just written that 7805. Then at this point we have ceramic capacitor, which is actual the main functions of it is to reduce the noise in this we call it pulsating signal on the we call it just, it means there's no pulsating signal actual, but just to reduce any noise. So its capacitance is 0.33 microfarad. Okay? Then here also we have another ceramic capacitor. So 0.1 microfarad. Then again, so we have one testing point. At these points also we need to have ground. And then this is the point where we have output voltage. Remember that for the power supply, we don't draw the output voltage maybe between the resistor and LED. No, we draw the output voltage from the output pin of the voltage regulator. Are we together? Joanna, can Kesha take Joanna's pen? So for that case, we say that, if you do remember, we say that in case of the simulation, because this is in case of simulation, this is the point that we are going to connect your T. So this is another testing point B. So in this testing point B, what are we interested with? We are interested to measure 2 parameters. The first one, we are interested or we are responsible to measure the output current. Because this voltage regulator can actually sustain 1 ampere, maximum of 1 ampere, then it's better to use milliammeter. So in this testing point TB also we need to know the output voltage. So we'll have voltage across this testing point TB. And this we can call TOT VO. But this voltmeter for this case should be connected towards TOT ground. Make it daddy. Then we say that now we have a resistor. What the resistance of this resistor? Speak loudly. Speak loudly. 100 ohm. Okay? Then we say that this is our light emitting diode. Make sure that you know the schematic symbols of electronics components that you are using in a schematic circuit diagram. You may measure the potential difference across resistor or potential difference across LED, but it's not important. Okay? It's not important because we just need this one to indicate the presence of power. If you measure the output voltage, it's 5 volt, that's enough. So if it's 5 volt, you expect the LED to be on. Okay, so sometimes also you may say that just I need, okay, it's fine. If you need to measure the voltage, you want just it's fine, but it's not important. And what the color of this LED? Blue. In the quiz that I gave, it's not just compulsory to claim that this should be blue. It can be blue, it can be yellow, it can be red. We just chose. Okay? So you should not claim that, there is blue, where is it? No, don't waste much of your time. Okay? So if that's the case, we are done for the power supply. So for the power supply, we just have only 2 important testing points where we have to measure just the supply voltage or input voltage, output voltage, and output current. Why don't we measure currents at this point? Because there's no any current consumption at this point because there is no load. We can measure currents if there's a load that's consuming current or consuming power, right? Right? Then we go for the input. So for the input, we say that we need the pull-down resistor network. So how many pull-down resistor network? 2. So this is schematic symbol of push button. You should not use just this one. Then we have a pull-up resistor of 10 kilo ohm. Then we have to connect it to the ground. For this case, when you have been learning or you have been actually dealing with the input unit, we use the DC voltmeter to measure voltage across push button and voltage across the resistor. Nowadays, go and make yourself well. But you have to check the importance, the contributions of that signal that you want to measure. For this case, what are we going to supply to our half adder? Kankesha, now you took the Johanna's pens to use it. Take Kankesha's pen. Take it and pencil. So listen. You may say that this is another testing point that I need to know the voltage across push button. Fine. But, okay, it's fine. It will help you just to know that whether the state of the push button has changed or something else. Okay? So this will be our testing point because we'll have 2 states of the push button. So you'll know that if the push button is pressed, what the output voltage. If it's not pressed, what the output voltage. So this is our testing point C. Again, this is very important. This is the very important testing point to measure the voltage across resistor. Why? Because this is the voltage that we are going to supply to the OT, to the O gauge. Are we together? Are we together? To the half adder. Fine. Then we need another network. Another pull down resistor network. So this is testing point what? D. So then we have this one. So this will be push button number 1. This will be resistor 1. This will be resistor 2. This will be push button 2. So push button 2. And then this will be resistor 2. You say that we're going to use 10 kilo ohm. Again, we need to measure the potential drop. VR2. And also for this point, we have voltage V voltage across what? Push button. So this will be our testing point what? A, C, D, E, and this one is what? F. This is DC voltmeter, DC voltmeter, DC voltmeter, DC voltmeter, DC voltmeter, DC voltmeter. Why? Because you are going to measure voltage, not millivolt. Are we together? Are we together? Then we have our exclusive O gauge. Remember that we don't have any exclusive O gauge which is like this. It does not exist. So again, some students, they might not think or relate about what is happening to the pull down resistor network, and then they say that this here we are going to have as a testing point. No, there's no need for you to have testing point at this point or in this input and this one, because you have already the test point for this input A or maybe input 1 and input 2 is this one and this one. Okay, when you connect them. So for that case, you say that, so let us connect what you have in pull-up resistor network. So this we call input 2, and the other one we have to okay. Again, we have the output of the sum. For the output of the sum, what are we interested in? We are interested with output DC output voltage of the sum. So we have to connect DC voltmeter. So DC voltmeter. So this one, let's say that we can call it VA. V8 means that voltage across half adder. This testing point will be called what? What the letter? A, B, C, D. E, F. So this is what? G. But this one should be connected to what? To ground. Abdullah. Again, we say that we like to know in this testing point G, also like to measure the output current of the OT of your half adder or of the sum part. Why? Because that output current might be the input current for the next C system. So it's better to know the magnitude of current. If it's actual, it will be convenient, it will be enough maybe to trigger the next C unit. Because this is just a part of electronics communication system. As I say that, the output of the sum will be might be fed into another system. So the issue of current, it's important. And this one we also encounter in most of integrated circuit. For instance, you cannot connect a DC motor or a stepper motor or a servo motor directly to the microcontroller. It will never rotate. Why? Because of current, not because of voltage. So then we need some indicator where we had resistor, and what the resistance? A? Students, I'm talking to you. You have that schematic. I don't have, for myself, in my brain. And I told you that one of my weaknesses is cramming. What the resistance of this resistor? Jacob? 200 ohm. Then we have another light emitting diode. Some students used to draw this one as a light emitting diode. This is a diode. Some students used to draw this one as light emitting diode. This is not a light emitting diode. This one, it's a one that we call light emitting diode. And then we have what? Ground. So to measure the voltage across this current limiting resistor, you may do it, but it's not important. Similar to measure the voltage across, what the color of this one, red? Green. Also to measure what? To measure the color of this one means that we call it just, it means that, to measure the voltage across LED, it's not important. Class, are we together? So we are done for the case of 40 of the sum. Let us wait for the part of 40 of the carry. So for the case of the carry, we don't bother ourselves. So what should we do? This is our input, our first input. Oh, sorry. Then this is our second input. Okay? So there's no need for you to measure the input 1 or the voltage or maybe the current of input 1 and input 2. Why? Because we have done the measurement. Remember that the voltage across input 1, the voltage across input 1 is actual voltage across 10 kilo ohm. The voltage across input 2 is actual the voltage across 10 kilo ohm. Okay? Okay? Then for this case, similarly, we also need to have another testing point. Another testing point. This is what? VB, let's say. Then we have what? Connect to the ground. This is GH. Shane, is it H? So then we have our light emitting diode. So how many testing points do you have? 1, 2, 3, 4, 5, 6, 7, 8. Okay? Okay. So this is figure 1, the measurement of overall schematic circuit diagram of half adder. Are we together? Pardon? You can connect the oscilloscope. What's wrong? How can you connect it? Simple. So with oscilloscope, one lead will connect it here. And this is your digital oscilloscope. And then this lead you'll connect to the ground. So this one will display the input waveform. It depends the channel. It display the input waveform of input 1. Or it will display the waveform of input 1, of the digital signal supplied at the input 1. If it is two-channel oscilloscope, then also the other channel will connect to input 2 or to input B. Then we need to use also digital oscilloscope to study or to observe the waveform of the output signal. So here you have digital oscilloscope. So the output signal. So then similarly, this one or this side you will connect to its ground, and for this side you have to connect it to the output. So you'll see that at this point you'll be measuring output voltage, output current, and also you observe the waveform on the oscilloscope. Are we together? Kevin, are we together? Are we together in what? Similarly, you will use digital oscilloscope to observe the input waveform and the output waveform. Okay? Okay. Remember that in simulation, we have just a single digital oscilloscope which has 4 channels. But actually, in real sense, or the digital oscilloscope that we have in our lab, they have only 2 channels. So for this case, it means that you will need one digital oscilloscope and the second. So this one, another channel for this one, you may connect the outputs of this point. So we just need 3 digital oscilloscopes to observe the waveform. Are we together? Are we together? So then, now the questions come. How does this system operate? How does it work? Because in previous workshop, we just do it. How does it work? Yeah? How does that system work? Because we just drew. How does it work? How does it operate? Eh? Students, I'm talking to you. You told me you understood, and Glory now is chatting. How does that system work? To add the binary input. You don't know. You don't know the principle of operation for that system. Class, I'm asking you. You don't know or you know? Eh? You know it. You know the principle of operation. I want to know. You know the principle of operation or you don't know? You don't know. Okay. Let me teach you. So, the assignment that I'm going to leave to you, or just the homework, draw the overall schematic circuit diagrams of half adder in hardware implementation, and choose the testing points. Also connect the measuring instrument. Remember that having a digital oscilloscope does not add testing points. Why? Because this point is connected with this point. So this is the single testing point. So at the testing point D, you'll have to measure the voltage, and also you'll have to observe the waveform for the input 1. Are we together? Are we together? This also is not another testing point. This one. It's not another testing point. Why? Because this point is just connected with this point. With this point. With this, which one? This one. Sorry. This one is connected with this one. This one is connected with this one. Also, this one is connected with this one. So this is the same testing point. Also for the same case, if you have a dictoscopes at this point, also you will have just a single testing point. So having the dictoscopes and connecting at the same testing point, you still have one testing point, but you are going to measure or to observe or to examine different parameters. Class, are we together? So now, the homework is draw the overall, because you just see transforming the integrated circuit. That's all. The overall schematic circuit diagram or logic diagram of hardware implementation. Of 40 half adder. Then I will end this workshop by just teaching you briefly about the principle of operation. Principle of operation of 40 half adder. So the principle of operations of this half adder depending on the truth table of half adder. Are you together? So what do you say? I will not write much. I will talk much rather than writing. So stop writing, listen, watch. This is the truth table. Truth table 40 of half adder. So in this truth table, we say that for the input, we have how many? We have 2 columns. For the outputs also, we have 2 columns. And then we say that, So this is input, this is our inputs, this is output. Then we say that, okay, can call it this is input A, input B. Then this is sum, this is carry. We use the example of Angelina and Namvua. So for this case, we say that Angelina did not go to class. Also, Namvua did not go to class. Angelina went to class. Namvua did not go to class. Angelina did not go to class. Namvua went to class. Both Angelina and Namvua went to class. Then we say 1 plus 1. We find what? 0, we carry 1. 0 plus 1, we get 1, we carry 0. 1 plus 0, 1, we carry 0. 0 plus 0, 0, we carry 0. So now, Johan, the principle of operations of this circuit is just like this one. I say listen and watch. Let us discuss about verifications of this row. Okay? Okay? You are the one who has to define that, because for this case you say that actual we have 2 states. So you can define that. So we can call it key that the binary number 1, we say that when the push button is pressed. This is binary number. The binary number 0, we say that this is when the push button is not pressed. So those are the two logical states for this case. If you are discussing, if maybe in this pull down resistor network you have sensors, so you can say that this one represents when the sensor detects the signal, and 0 represents when the sensor does not detect the signal. That's all. So those are the scenarios that we have in digital electronics. Adamu, T, Yuma, what did they say? So for this case now, let us start with this. So suppose this is push button number, push button A, push button B. Okay? Okay? So how can we verify this one? It means you say that push button A and push button B have to be pressed. Now means they should not be pressed. So to have this state, it means we say when the push button A is not pressed, and the push button B, or where so we say that when the push button 1 and push button 2 are not pressed, then we expect it that's the principle of operation. So what do you expect? We expect it that the blue LED to be off, while the green LED to be off, represents some, and this is what red here. The red LED will be on. Should I repeat? Should I repeat? Listen, concentrate. Simple. We say to verify this column. Say that column, first column. No, say first. Say second row. Okay, let's say first column with Boolean values, because this we call them Boolean values. So we call first column row with Boolean values. Say Boolean values. Boolean values are just 1 and 0. That's all. So to verify, how does this circuit operate to verify the first row? Right? We said the binary bit 1 represents when the push button is pressed. And here, when the push button is not pressed. That's what we define. You may do, it means you may define vice versa. Are you together? So to have 1, then the push button A, so suppose that this is the push button A, and push button B, they have to be pressed. Why should we press? In order to get binary number 1, just like you have here and here. What will happen when we press them? So when this exclusive OR gate add 1 and 1, the output is 0. Okay? So because the output is 0, it will turn off the LED, the green LED. While at the same time, it will turn on the what? The red LED. Okay? Okay? Then the second row. Remember that 0 represents when the push button is not pressed. So he said that the push button A is not pressed, or while the push button B is pressed, that causes or that results what? The green LED to be on, while the red LED to be off. Are we together? Joseph Pasco. Then we are going to verify the steady row. So how can we verify? For these binary bits, we need to press push button, right? Push button A. For this one, we should not press. Or vice versa. Yes. Okay? So we have to press what? Push button A. And release or don't press push button what? B. What do you expect as output? The green LED to be on, while the red LED to be off. Are we together? Are we together? Then verifications of the last row. How can we get these states with push button? Push button A and B are not pressed. The results will be what? The green and the red LEDs will be off. That's all. That's the principle of what? Operation. But you have to take care, because we did not measure the voltage for that case, so it will taper that across that once. Then you may, so sometimes, let me just define this one. You may also say that 1 represent that it depends to the output voltage across the resistor. When the push button, so this one, when the push button is not pressed. And then 0, binary bit is 0, we say that when the push button is what is Kuru? Is what is Kuru? Is pressed. Are we together? So you should not claim. These are not a material that you have to claim. You just need to understand once and then keep in your mind. Your brains, actually, that you are very intelligent more than this stuff. And your memory can save a lot of information. Class, is it clear? Yeah. So the same principle of operation, even if that you do the implementation. And this is how you test whether you are schematically logical circuit diagrams of half other work or it doesn't work. Okay? So let me leave another homework for this case. So the homework is draw the table of results. So draw the table of results of 40 of table of results of the half adder. Include calculated or theoretical values. Theoretical values. Theoretical, calculated or theoretical values. Simulated values. And they measure the values. This is no longer homework, it's an assignment. So I will need it by Tuesday. I'll need it by what? Tuesday. So you just, I think that I'll try to check arrangements if you can have this component, so you have to build. But in case that the workshops will be busy, you can leave the part of the measure, the values. But for the theoretical and calculated, you don't have an excuse. You have to find them. And what are the important parameters? Voltage and the current. Class, is it clear? Yeah. Okay. So if it is clear, did you understand? Okay, it's time to congratulate you. It's time to congratulate you for understanding. 1, 2, 3, Dixon Macha. Ongera. Imara. Wow. So I would like to say this is the end of workshop 4. And I would like to say that we have discussed about, we have even finished chapter 5. We'll go back to chapter 4, where that we have to discuss about how we can build the real-time RF transmitter and RF receiver. So this is the end. Make sure to go through these contents. And in case you have a question, let me know, or let us share together. And make sure to do all of these tasks that I have given you, because they will add the value in your process of learning. So I would like to say that thank you very much. See you in the next time. May God bless you.
Africa. Africa.